Hello everybody, welcome to the Area Volume FRQs from AP Calculus AB. I've selected two FRQs from older exams just to kind of go over and review some concepts with you. The two that I've selected are the 2019 Area Volume question, but also the 2014 Area Volume question. So stay tuned to take a look at that one. One of them is non-calculator. That would be this one. As you can see, it's number 5. And then, of course, we have the 2014 question. I believe that's number 2, indicating that it is a calculator active FRQ. Let's begin. Okay, this question says, let R be the region enclosed by the graphs of g of x and h of x, the y-axis and the vertical line x equals 2, as shown in the figure above. So we have here the line x equals 2. We also have the vertical line at the y-axis, which is x equals to 0. And then we got to just determine which function's on top and which function here would be on the bottom. So for that, we have to just kind of observe function behavior. So I noticed that this is a quadratic. This -2 indicates that it's concave down. And so that looks like it's going to be this function here on top, right? So that would be the h of x function up there. And then that means that g of x appears to be on the bottom. All right, so that's going to be pretty helpful. So the first question says, find the area of region R. Well, whenever we're finding the area, we need bounds, right? So we're going to set up an integral here, which is just going to be the integral, which appears to go from 0 to 2. And then we always put the top function minus the bottom function. So I can see here that the top function is h of x minus the bottom function, that's g of x. And then the variable of integration is dx. So I'm just going to go ahead and say dx right here. All right, now keeping in mind that this question is non-calculator, we haven't really found the area. All we did so far was just, set this up to find the area. So of course, we're going to have to find that area. Okay, all right, so let's continue that down here. All right, well, good news is if you have properly written the integrand that year, they give a point for that. So that's good news. All right, let's go ahead and keep working with this, right? I'm going to plug in the functions just because I'm going to have to take the antiderivative here. So let's just plug everything in. We have 6 minus 2 times x minus 1 squared, right? That's our h of x, minus our g of x. I'm going to just go ahead and distribute a negative to everything. So negative with -2 makes a +2. Negative with this cosine term makes a -3 cosine of pi over 2x, right? All of that has that variable of integration of dx, right? Okay, so I'm going to keep simplifying this as we go a little bit. So I can see here that this is just going to be, we got that 6 plus 2, that's 8. Alrighty, we have this term, which, I mean, you could extend it out a little bit, expand it, better said. But ultimately, we could also just keep it like this, right? Nothing wrong with that. And then we have this -3 cosine of pi over 2x, right? Okay, so there we go, dx. Now, so far, I haven't really done anything besides just plug in these functions. So I'm still locked into that first point of the integrand, all right? From here, I want to start taking the antiderivative of each term, all right? So I'm going to go ahead and say, well, this is really I'm going to split this up. This is the integral from 0 to 2 with 8 dx, right? And I know that I can then, add or, of course, subtract this. So I'm going to take out that -2. And then I'm going to take the integral again from 0 to 2. And all I have left here is that x minus 1 squared, again, dx. Okay, and then I have this -3. Okay, well, I'm going to take out that -3 and then take our integral again from 0 to 2. And then I have just that cosine of pi over 2x dx, right? So what I did here is I just split it into a couple different integrals. And now I'll just integrate these separately. All right, so we know that the antiderivative of 8, of course, is just 8x, right? We're going to be evaluating that from 0 to 2, right? Over here, we could use a u substitution, right? And if we do that, let's change colors, then we could say that x minus 1 is going to be u. And then from there, we just integrate that. So let's do that here. Let's say that x minus 1 is going to be our u, which makes that du is equals to just dx. Alrighty, and anyway, we're ready to go from here, right? Okay, so I'm going to just replace this so that it becomes, let's do this on the side. Let me keep the pink going. Keep the pink alive, right? All right, so we got this, this integral that goes from 0 to 2, of course. And then we have u squared, right? And instead of, that's this part here, u squared. And then instead of writing dx, we'll go ahead and write that du. All right, now power rule on this, that makes this u to the third over 3, all right? And we'll just evaluate that from 0 to 2 as long as we plug in our u, but keeping in mind that we got this -2 we want to distribute. So that makes this -2 times, let's replace that x minus 1 cubed over 3. And then, of course, this gets also evaluated from 0 to 2. And then the next term here, also u substitution, because we have cosine of pi over 2x. Alrighty, so let's see if I can squeeze that in here too. U substitution, let's make our u pi over 2x. All right, and so when we do the du, this is just going to give us pi over 2 dx. And now I like to isolate the dx, so when I do that, I'm basically just going to multiply by the reciprocal, 2 over pi. So then what I do to one side, remember, always do that to the other, and you end up with that du right there, okay? All right, so this is our dx. Okay, well, what do we do from here? Well, let's integrate. Let's see. We got that integral that goes from 0 to 2, cosine of u, right? And we said that dx, where's that, is equals to du, but we have this 2 over pi. So I'm going to put that 2 over pi here because that's just a constant. And then in the front of the 2 over pi, notice we had that -3 out there. So if you want to go ahead and multiply that by -3, I don't think when I did the pink one here on the side, I don't think I did that earlier, but it's only because we already have a constant with the u substitution. So anyway, that's what I'm going to do from there. And now we're going to integrate this. And so the antiderivative of cosine is actually, in fact, going to give us just sine of u. Remember that u is really this pi over 2x, and then we'll just multiply by that -3 times 2, which is -6 over pi, okay? All right, so let's plug all that in. So we got this -6 over pi sine of pi over 2x. All right, let's write that in. Pi over 2x, right? And then that goes also from 0 to 2, okay? All right, so I know that I've done a lot here, but let's talk points. So that we just took the antiderivative of this cosine of pi over 2x. That was given as a point, this thing here that I wrote in the light blue. And then the antiderivative of the other terms was also given as a point. All right, so that's good. That's 3 points so far in part A. That year, of course, remember this is the 2019 FRQ. So we're going to be just kind of observing where the points are given, which is really important because it kind of helps you understand how, the AP readers award credit, okay? Anyway, from here, you're just going to use your fundamental theorem of calculus to plug in your upper bounds and then minus plugging in your lower bounds, and we go from there, okay? All right, so let's see what that looks like. If we plug in here, 8 times 2, well, that's going to give us 16, right? But then 8 times 0, well, that's just 0. Okay, bingo. Now, let's plug into this next term. If we plug in 2, let's see. I'm going to write here -2 times x minus 1 to the third power. Okay, well, what is x? 2, right? So 2 minus 1 is 1. So that's going to be 1 cubed, which is just 1, right, over 3. And now, what happens when I plug in 0? Okay, well, when I plug in 0, don't I just get here, let's see, 0 minus 1, that's -1, but -1 to the third power, oh, that's -1, but -1 times -2, oh, that's a +2, right? Okay, so, oops, so 2 over 3 is what we get out of that one, okay? And let's see, keep going from here. Okay, now we are going to plug in the 2 into here. Well, 2 over 2, that should cancel, giving you just pi. And so when we think about what is sine of pi, remember that pi falls here on the unit circle, right? And so, and then from there, sorry, my drawing, the coordinate here is -1, 0, and so sine of pi is actually just 0. Okay, well, 0 times whatever, that's just 0. Well, what happens when we plug in 0 for x? And when we plug in 0 for x, 1 comma 0, and then that's also a y value of 0. Sine is the y coordinate here. Okay, so that also gives me 0 times 6 over pi. So look, this is what we get here. So even though we got 2 over 3, let's keep in mind that we're going to subtract, right? It's always the upper bounds when you plug that in, right? And that gave us, of course, that negative 2 over 3, right? And then minus the lower bounds. So I plugged in 0 here, and we got negative 2 over 3, right? Well, we got here negative 1, negative 2, right? Okay, so that's 2 over 3. But remember that we're always subtracting with this lower bound. So even though we have it plus, let's make sure that we're always subtracting that. So I'm going to go ahead and remove that plus and just make it turn into a negative, okay? All right, so this gives me 4/3, but remember that on a non-calculator FRQ, you don't have to simplify this. So you could leave it as 16 minus 4/3 if you like. You could have left it like this if you'd like. Either way, that would have been fine. The final answer here should be 44 over 3, but not necessary to simplify. So any one of these versions, which is technically equivalent to 44 over 3, that gives you the answer point. So this part of the question here was worth 4 points. Again, 1 point for the integrand, 1 point for the antiderivative of that cosine of pi over 2x term, 1 point for the antiderivative of the remaining terms, and of course 1 point for the answer. All right, let's look at part B. So for part B, the question says region R is the base of a solid. For the solid at each x, the cross section is perpendicular to the x-axis, has an area of a of x, which is 1 over x plus 3, which that just means that the cross section looks like, whoops, that's not vertical. The cross section looks something like this, okay? And they're telling us the cross section is perpendicular to the x-axis. Okay, so that means that this is dx for sure, all right? Anyway, they're giving us the area, so we don't have to calculate the area to figure out the base and all that fun stuff, okay? Find the volume of the solid. Well, remember that the volume is always the integral of the area. So the limits of integration are still going to go from 0 to 2, but it's going to be the integral of the area, which in this case would just be a of x dx. Okay, so that's good. Now, that's your setup basically, right? Well, what is a of x? Because we have to find the volume, right? So this is just a setup, which if you're wondering if you got points for this that year, yes, students that wrote this in got the integral point. Another version of this would be to say 1 over x plus 3, actually plugging that in, right? Dx, that also is equivalent to the first point for the integral. But now, can you actually come up with the answer, right? So when I see, 1 over something, I'm thinking, natural log here. Feel free to use a u substitution again. This might be overkill, but anyway, if we set up u substitution for x plus 3, then that means that du is just equals to dx. And then when you go to jump in with this, you're like, oh, well, I know that this is going to be the integral from 0 to 2 of 1 over u du. And then you're like, oh, wait a second, I know that that's just ln of u, right? And so, what is u? Oh, u is just x plus 3. So then that helps us say that this is going to be, ln of x plus 3. I put it in parentheses, my mistake. It should have been in brackets, okay? So this is ln of x plus 3, and then, the limits of integration are from 0 to 2. Another way to write that is to just put this bracket and just go 0 to 2 like that. It's kind of equivalent to what I did up here. And anyway, now we'll plug in those, those values, right? The upper bound was 2, so 2 plus 3 is 5. This gives me ln of 5. If we take the absolute value of 5, it's still 5. And then minus, if we plug in 0, 0 plus 3 is 3. Well, with its absolute value, still 3. So this is what we end up getting, ln of 5 minus ln of 3. Okay, I'm going to box this. And I actually did not box the last one, but this is the final answer. Remember, you do not need to get to the final answer. In this case, you do, because we still need to plug in the bounds, right? Okay, so in part B, let's talk points. 1 point for that setup, right? Did you get the integral correct? 1 point for the answer. That one was kind of easy, right? All right, let's take a look at part C. It says, write, but do not evaluate an integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals I'm sorry, y equals 6. So where is that? 1, 2, 3, 4, 5, 6. All right, so let's keep this pink alive, right? Okay, and then this is the rotation of the line, y equals 6. There we go. So as this thing rotates around, we're creating this solid, right? And I can see here that we definitely have a washer method in this question. Okay, so from the axis of revolution, I'm just going to use this part here. The outer function, also known as the function that's going to create a bigger radius along that axis of revolution, right? It's circular. I like to call that big R. So I'm going to just say R of x, right? Now, what is that? Well, what is the function? That's g of x. So I like to take my function g of x, but it's not just g of x. You see, always subtract by your axis of revolution. That's minus 6. There you go. Now, what is little r? Well, what's the small radius as you rotate this thing around? And from here, the axis of revolution to the inner function, that's going to be this function. It's a little closer. I'll just draw that here so you can see it. And that right there is little r. So I'm going to put it here as little r. And then little r is that function, which is h of x. And then minus the axis of revolution, which again is just 6. Okay, so let's keep that in mind because now we have to do the whole right, but do not evaluate an integral expression that gives the volume of the solid. Okay, so I'll work that one out up here. Okay, so when you rotate around, remember volume is always the integral of the area. And what is the area of something that's rotating around? What shape is that? That's a circle, right? So what is the area formula of a circle? And that's pi r squared. So whenever that you get that type of question, there has to be a pi in your formula for volume, okay? So one of the things that we like to do is we like to take that pi out because that's a constant, okay? And then we'll set up our integral, okay? That way you don't forget about that pi. All right, so what are the bounds? Well, we have a lower bound from 0. We have an upper bound of 2, so let's throw that in there as well. Okay, and a lot of times you get the points just for writing that constant and the bounds correctly, but there should be some context in here as well. All right, so what do we got? Let's see. Well, it's always the top minus the bottom, but what, right? Because it's area. Well, we know that it's going to be it's pi r squared. So, what is r? Well, we have r here. So it's pi r squared, that's the big R, right? Minus pi r squared, and that's the little r. So that's exactly how I'll start this, all right? So, I mean, technically you could write that this is just, r of x squared minus little r of x squared, especially if you went ahead and already identified what is big R and little r, right? We would accept that. But more importantly, wouldn't be a bad idea to just plug in what is big R, what is little r, okay? So let's rewrite this. All right, so what is big R? Okay, we said that was g of x minus 6, right? Square that, because again, it's pi r squared. All right, so I'm going to put brackets around this thing, squared, minus, and then little r squared. Well, that's just h of x minus 6. Okay, let's put brackets around that. So square that. Again, pi r squared minus pi r squared. Okay, and then variable integration, that has to be there. Remember, that's just dx. So I'm just going to put another bracket around all of this and dx. All right. Woof, that was a lot. Remember, this is a washer method, so it takes a little bit more thinking, right? Okay, so where are the points? There's 3 points left, and 1 point comes from the limits and the constant. That's what I talked about, the pi and the lower bound and upper bound here. The form of the integrand is the next point, and then the last point is well, the integrand, right? We didn't have to get to the answer, so that's where the points are distributed here, okay? That wraps up the 2019 FRQ. Now let's take a look at the 2014 FRQ. And this one is calculator active because I can see here that it was question 2. All right, so let's get into this one. Let R be the region enclosed by the graph of f of x and the horizontal line of y equals 4. Okay, so we know a horizontal line, that's this guy here. And well, this function, we see it on the graph. Okay, so this thing here has to be, let's just label that as f of x, okay? Awesome, okay. Now, find the volume of the solid that's generated when R is rotated about the horizontal line y equals -2. Okay, so where is that? Let me see. Okay, so let's just say -2 is down here. right? Okay, I'm going to spin this thing around. And as this graph spins around and around and around and around, what's going to happen? Well, what's going to happen is that it's going to create a washer method, right? So, well, what are those pieces? Well, okay, so let's see. We have from the axis of revolution, the outer function, which is going to be what I like to call big R. All right, let's put that here as R of x. And what is little r, the little radius, as this thing spins around and around and around? Okay, so let me see. This is a washer method, right? So this right here is little r. Perfect. Okay, so what is big R and what is little r? Okay, so let's see. Big R is always the function. So what is that function? Oh, that's just going to be 4. Okay, 4 minus the axis of revolution. Well, the axis of revolution appears to be -2, so 4 minus -2. Well, that becomes 4 plus 2. Oh, okay, so 4 plus 2 is going to give me 6. That's interesting. Okay, and then from here, we can go into the little r, right? So little r is going to be, let's see, what's that? F of x, right? Minus the axis of revolution. Okay, so that's f of x minus the axis of revolution, which again is -2. So I'm just going to put -2. And again, that minus with the negative, that becomes plus. So this means we really get f of x plus 2. All right, so I hope that makes sense so far. But again, this is a washer method. Find the volume means integral of the area. And so area of a circle is pi r squared. But we got to do r as far as like pi r squared minus pi r squared, because we have 2 circles here, okay? And so what we're going to do is take the integral. This one goes from here to here. We'll find those bounds in just a minute. Don't forget about your pi, because we're spinning around and around and around, right? Okay, but we can go ahead and start plugging this stuff in, right? Okay, so what is this going to be? Well, this is going to be, 6, right? So that's the big R. Oh, okay, it's a big R squared minus, and then little r squared. Oh, that's just f of x plus 2. Perfect. And I want to square that. So that's pi r squared minus pi r squared. All I'm missing here is that dx, and of course, the limit of integration. So, all right, well, let me see. It looks like they're going to intersect here at 0 and some point, which unfortunately is not marked in this graph, but that's why this question is in fact calculator active. So let's get that calculator going, and let's put this function in the calculator, right? Okay, so I know that I have the 4. I like to put the top function as y1, and I'm just going to go ahead and put y2 as that function, which I also see in there. Perfect. Okay, and then once we have that, we are able to, let's see, take a look at the graph. I have no idea what I'm looking at there. Okay, so I might want to zoom in a bit, huh? Okay, so let me hit window. Let's see what we're looking at. -10 to 50. Oh, 50 is a lot, right? So I'm going to do something. I'm going to hit zoom, and I'm going to hit standard. That'll take you to the standard window of the calculator, and that looks a little bit nicer. Okay, so even though it's still kind of zoomed out, I can kind of get the idea of where these 2 intersection points are. So let me use that. I'm going to hit second, and I'm going to hit calculate. Let's calculate the intersection of the 2 curves, right? Okay, so as you go left to right here, notice that on the top where it says calculate intersection, right below it says y1, which just means that my calculator is currently hovering over the y1 function, and I just need to select one of the curves that I want to intersect. So anywhere is fine. Now all of a sudden it defaults to the next curve. Okay, that's the red one. Perfect. I just need to select it. It's giving you instructions at the bottom of the screen. And now guess, what are we calculating? Oh, the intersections, right? Okay, so move your way over to the intersection, and it'll tell you that it's actually that number, which if you move the decimal, the 5 units, that's basically 0, isn't it? Okay, so we're going to go 0 to what, right? Okay, so now let's do the calculate intersection again, which is over here. All right, so let's do second calculate, and again, intersection. So I'm just going to hover over this thing. Okay, first curve and second curve. And now I got to maneuver the calculator. Oops, too much. Oh, look. I go over, I go under, right? As long as you're in the ballpark and you've already selected the 2 curves, it'll calculate that intersection point, okay? As opposed to the other one. So 2.3 is what I'm getting. So we're going to go from 0 to 2.3. All right, so let's do that again and write the limits of integration. So from 0 to 2.3, okay? All right, so this is what I got for part A. This is my setup, all right? That's good, right? So now what I want to do here is I want to be able to plug it in the calculator with these numbers. Okay, let's put our pi in there. Again, math 9, and then we go from 0 to, we said 2.3. All right, okay, what are we doing here? 6 squared. I mean, if you have the withedness to say that that's 36, that's cool. Okay, minus, now open a parentheses to go ahead and put f of x plus 2. Remember, we set f of x as the y2, so you can go ahead and select that from your calculator to save yourself some time. That would be alpha. Up here f4, those are, think of that as functions, okay, and just select y2, and then I'm just going to put here plus 2. I'm going to close that parentheses and square it. There we go. And okay, that outer parentheses is there, and then we throw our dx at the end, okay? All right, so let's see, we got 98.868, all right? You can also say 98.867, that would be fine as well. Okay, and those are the two acceptable answers for this question. Okay, all right, so let's talk points. You get 2 points for the integrand this specific year. Again, this one goes way back to 2014. 1 point for the limits, that would be the 0 to 2.3. And then 1 point for this answer that you're staring at right now, 98.867 or 98.868. Okay, remember we can round or truncate on the Calc AP test. All right. Okay, let's take a look at part B. Part B of the question says region R is the base of a solid, and for this solid, each cross section perpendicular to the x-axis is an isosceles triangle. What? Okay, so again, perpendicular to the x-axis would look like this, which just tells me that this is a dx question, like I said in the last one. Okay. All right. With a leg in R. All right. Find the volume of the solid. All right, so, well, remember that the area formula, I'm just going to write it as A of x. Okay, so we know that the area of a right isosceles triangle should be half times base times height, and because it's an isosceles right triangle, these two are the same, base and height, so it's like saying base squared. Okay, so I'm going to just write here half times base squared. And remember that in order to find the base, you take the top function and you do minus the bottom function. All right, so, well, our top function is the 4 and our bottom function is f of x. So let's plug that in, right? So this is going to be the integral that goes from the 0 to 2.3. Remember that those intersection points that we found earlier, or we're going to be using them pretty much for the entire question. So that was golden to find. And all right, let's plug everything in. So we know that this is just 1/2 times the base times the height, which just means base squared in this case, because again, it's a right isosceles triangle, but then a leg has, one of the legs is in R, right? So that again means that base is squared. Anyway, and then from here, what is the base? Well, what is the top function? We said that was 4. Okay, so I'm going to put parentheses 4 minus the bottom function. We said that was f of x. And again, square that, okay? So I'm just going to close this parentheses up, square this. And because there's a variable of integration of dx, let's put a bracket around all of this, throw that dx at the end. And okay, well, that's our setup, right? Now, if we have to find the volume, like this one, well, we need to get the value, okay? So that's going to go in the calculator. And if we put this in our calculator, let's see, we go math 9, right? Again, 0 to 2.3. And then we'll just plug everything in, right? Okay, so this is a 1/2, which you could technically throw in the front. If you forget to, at the end, you can always divide by 2. That's cool. All right, I'm just going to put here 0.5 and then times, so I'll open a parentheses so that I can put that 4 minus the f of x. Remember, that was our y2. So alpha, again, select that function 4. So you can put your y2 in there. So that's 4 minus f of x. Close that parentheses because we need to square it, right? And then there's that outer parentheses here, right? Okay, but are we good? Are we good on the parentheses? Yes, we are. Okay, so now I'm going to just go dx, all right? Perfect. And I get 3.573 or 3.574, all right? So let's talk points in part B. The integrand was worth 2 points in 2014. all right? And the answer was worth 1 point. So 4 points from part A, 3 points in part B, all right? That's already 7 points with only 2 more left that has to go to part C, okay? All right, so let's get started with part C and see the point breakdown there, okay? I'm just gonna change colors to make it a little easier to read. And I might wanna erase some of these markings just so that everything is also easier to read. All right, we don't need any of this anymore. Now, unfortunately, on the AP exams now, they're hybrid. I'm sure in the future they may go to completely digital, but this is the year 2026, as you can see at the bottom of my screen there. And we are currently doing Calc AB exams in a hybrid form, which means that you're going to see the questions on the screen, but you're going to have an answer booklet where you're recording your FRQs. So this diagram is not given to you. So one of the things that I recommend to my students is, you know, I would like the ability to doodle on these graphs. And unfortunately, that's not a feature that's available right now on this platform that we use for testing. So just make a quick little rough sketch of it, of the graph, you know, that you're given, and just kind of use that to doodle all over on your work, okay? You know, if you have that scrap paper, use that to doodle, okay? Because this is going to be really important. You can see how many markings I made, especially on this particular FRQ. On other ones, not as much, but this one, you really got to write all over it, okay? So I'd love to see College Board put the doodle feature on these things, but you know, these things take time. So hopefully in the future, that's something that we can see. And College Board, if you're listening, let's make it happen. All right, so the part C, the vertical line x equals k divides R into 2 regions with equal areas, right? Right, but do not solve an equation involving integral expressions whose solution gives the value k. All right, so what are some important things here? So there's a vertical line now, a new one, right? Oh, x equals k. Oh, well, what is that? Where does that go? Just anywhere? No, it divides it into 2 equal areas. Okay, so let's slice this thing down the middle, right? And this is x equals k. Well, what is k? Well, we might have to find that, right? Maybe not. Let's read on. Right, but do not solve. Oh, maybe we don't have to solve after all. An equation. This is what got everybody that year. An equation involving integral expressions whose solution gives the value k. Oh, okay. So since they're equal, if you remember from geometry, the congruent mark is nice, right? We can go take it back. And that means these things are equal, right? Okay, well, how can I represent that? Well, I could say that oh, wait a second, I lost my my graph now. I could say, there we go, that's good. Okay, I could say that I want to take the area of this like first little region here, and then the area of the second region. I know that they're equal to each other because again, they're equal areas. All right, but I just need before it was from 0 to 2.3. Now it's supposed to be from 0 to, oh, k. Well, I don't really know what k is, and I don't think I need to solve it because it says write but do not solve. Maybe I can get away without solving it. Let's see. Well, the first area, it's going to go from 0 to k, right? And it's going to be the top function minus the bottom function, right? Because it's asking for area, 2 equal areas. Okay, so the top function we know is 4, and then we know that the bottom function, well, that's just f of x. So I'm going to say here 4 minus f of x squared, right? No, just 4 minus f of x. 4 minus f of x dx, right? And then that's supposed to equal now the other area, which looks like the lower limit will be k now, but it goes to that 2.3 that we found earlier. So now that's supposed to equal the integral that goes from k to 2.3, and again, top minus bottom. Well, that still appears to be 4 minus f of x, okay? Close that parentheses and throw that dx at the end. All right, so let's talk about points. 1 point here was given for the area of one region, which a lot of students wrote an expression. They didn't quite catch the equation part. I know that there's a lot to digest in questions like this sometimes, and that's why the points are distributed, you know, generously throughout the question. And then the second point here came from the equation. Did students actually grasp that the areas were equal? Did they write the equation, and was it correct, obviously, okay? Anyway, that wraps up the 2014 FRQ on area volume. This was number 2, and this one was calculator active. And even though it was calculator active, you can see that this last part C, it didn't really require the use of the calculator. So not all parts will require that. It's just that, you know, the majority of the answers will require you to use your calculator to get to that last step. Okay. But anyway, I hope this was helpful, and I hope that you all have a better understanding of this area volume FRQ. This is one that we see almost every year, but sometimes it's calculator active and sometimes it's not. So one of each wouldn't help to kind of work through it and make sure that you understand. Remember that you also have access to the last 3 years FRQs, usually on AP Classroom if you've already enrolled. And I hope that that helps you kind of pick up on a trend that we're seeing the last couple of years. I picked a couple older ones just to kind of show you that this is something that we always see. All right, it hasn't gone away yet. And anyway, all right, hope that was helpful, everybody. If you're liking these videos, I have another one on motion, and I'm going to try to do the rest of the FRQs pretty soon. Feel free to subscribe, and hopefully you get what you need from my channel. Thanks for watching.